Hey guys, first we're going to make sure this is marked accordingly. So you're going to make sure you have the right page of the midterm, and you're going to write on here homework number 1 for quarter 3. It is quarter 3. And make sure you put your name on this paper, and you're turning this paper and only this paper and or something stapled to it. And I'm going to look at the front of the back and that extra sheet. So let's do it. Okay, so let's see. It says, let's just start all these are kind of different ordered. So let's start at this one. Box plot has 2 data sets. So a box plot is a 5-number summary. It gives you the minimum, the maximum, the middle number, the middle of the bottom half, and the middle of the top half. So usually they just have you compare these 5 numbers that they're summarizing. It says the range of both plots is about the same. So the range is, so let's say this was 20 and this was 100, right? This looks like it would be, I don't know, 50 and 130, right? You see what I'm saying? The range is max minus min. Range is max minus min. So in this instance, if it was the max was 100, and I take away 20, I get 80. So that's the width, or the distance between the max and the min. And this other number, this other plot data set, it looks like the max is about 130. If I put little increments along here, you see, and the max is about 130, take away 50, that's 80. Notice the width of these 2 box plots, whisker to whisker, is the same. So it's got to be A. Now, a couple people asked, well, what are, can you prove to me the other ones are wrong? Sure. The mean is approximately equal. Okay, so I'm going to tell you something. We can't tell exactly the skewness of this data, but it looks like I could fold this side on top of that side pretty accurately, meaning the left side of the box plot looks about the same as the right side. So what that means is if the left side of the box plot looks similar to the right side, and we have that approximately on the other one too, then this is symmetrical data. And what we know about symmetrical data is the mean is pretty darn close to the median. So what that means is the median is here, and the mean's probably pretty close to it. And the median of the other data set is here, and the mean of that data set is pretty close to it. So this looks very different to me. This plot 2, the mean of plot 2 is probably much higher than the mean of plot 1. So that would be false. C, plot 2 contains more data points. That is totally unknowable. We have no way of knowing. This could be 1,000 pieces of data, and a 5-number summary just summarizes the max, the min, the median, the middle of the bottom, and the middle of the top. So it gives you a 5-number summary of these 1,000 pieces of information, and this could be 100 pieces of information. We have no way of knowing. The medians are about equal. Well, we said back there, that's false. The median of plot 2 is greater than the median of plot 1. So that's no good, that's no good, that's unknowable. Plot 1 is more symmetrical. I can see how you might fall into this. It looks, both are roughly symmetrical. Okay, so there's a better answer, and A is the better answer. Both are roughly symmetrical. Let me know if you have more questions on that one. Okay, let's do another one. It says, a child is 40 inches tall. So I think I need another piece of paper for this one. Okay, child is 40 inches tall, places him in the 90th percentile. So whoop. It says it's approximately normal, so I'm going to draw a graph. This child's 40 inches tall, and that means she's in the 90th percentile. So that means 2 things. It means the area to the left of the curve, if the area under this curve is 0.9, then the area to the left of this curve is 0.9, the yellow stuff, and the area to the right of the curve is 0.1 because the area under the whole curve is 1. So that's what that means. So here's her height, and we're not sure what it is. Oh wait, we are sure. It's 40 inches. Now it says the height of these other children, the mean is 38 inches. Okay, so this is 40, and this is 38. Based on this information, what's the standard deviation? So we use our formula AP statistics. Our z-score is, what is her actual height? 40 inches. What would we predict if we knew nothing about her? Well, we'd predict any child is 38 because that's the average. And what's the standard deviation? Nobody knows. That's what we're solving for. So we can call that x, or we can leave it the variable s. Now what? Well, I don't know the z-score, but I know the area under the curve. So this one, I would go to the z-tables and just read. Look for the number, because the area under the curve or inside this region, and then scoot to the margins where you can find the z-score, okay? Now, I don't have a z-table on me. But I'm willing to bet if you looked at a z, I actually can just Google one on my phone, but my phone's videotaping this, so I can't do that. Right? I could also use an inverse normal. I know the mean. I don't know the standard deviation, but I know the area under the curve. Okay, so the mean's 38. The standard deviation, I could guess, is one of these numbers. So let's say you guessed that, and you know the area of the under curve is 0.9. And you can just keep changing this standard deviation until you get your answer. And again, you know your answer is the student is 40 inches tall. Okay, so that's how you'd work this backwards with an inverse normal calculator. Otherwise, you got to look at your z-score. Okay, so let's work backwards. And I'll tell you what let's see, I do have a book here. Okay, no, I guess I have this. All right, so this graph looks like my graph, and I'm looking for the number 0.9 inside here. 0.9032, 0.915. Okay, that number is the closest number to 0.9, 0.8997. So what's that z-score? 1.28. 1.28. Okay. So that's the z-score that correlates to 1.28 is the z-score that goes with the area to the left of the curve is 0.9. Okay, now we know 40 minus 38 is 2, and we have s. So why don't we just do our swap here? We put our s here, 2 divided by 1.28. Cool. Okay, so 2 divided by 1.28 is 1.56, and we have our answer. Awesome. Let's do another one. So this was AP 1.2, it's AP 1.3. A large set of test scores had a mean of 60 and a standard deviation of 18. Okay. So a typical person got anywhere between a 42 and a 78 because that's what standard deviation means. A typical score was 60 plus or minus 18. If each score doubled, so that means the average student that got a 60, if you were an average student and that was you, you now have a 120. If you were one standard deviation above the mean, so you did pretty good on average, we doubled your score too, so 78 times 2. And if you got a score of a 42, we doubled your score too. We didn't leave anyone out. We doubled everybody's scores. It says then, and then 5 is subtracted from the result. So take away 5, we get 79. Take away 5, we get 115. Take away 5, we get 151. Okay, so everyone's scores have been doubled and then subtracted by 5. What will be the new mean and the standard deviation? Well, the new mean is definitely 115, and the standard deviation is just the distance between this number or this number. So remember how we arrived at this. The standard deviation was 78 minus 60, or 18. And the standard deviation here is now 151 minus 115. Oops, 36. So it looks like my standard deviation doubled, but it didn't subtract, because when we did some activities in class, when we multiply or divide, our standard deviation changes, but it doesn't change when we add or subtract. It doesn't change. Standard deviation doesn't change when we add or subtract. Okay. So that's why that answer is 36. Hopefully that's sinking in. Let's do another. It says you look at a Florida real estate ad. In Sarasota, many homes have been priced at $200,000 to $400,000. A few of the houses on the water, however, are up to $15 million. So 0, maybe 100,000, 200,000, 300, 400, and then it fell off the map. There's like a $15 million home out here, Derek Jeter's house. Which of the following must be true about this distribution? Most likely it's skewed right. Even a single home valued at $15 million likely won't affect the median amount, but it will affect the mean. The mean will be pulled to the right. Now, what else? And the mean is greater than the mean. Well, that's why it's right skewed, meaning numbers go up on a number line when you move them to the right. So right skewed data means the mean is to the right of the median. Okay, next one. It says a linear regression was performed using the 5 data points, okay, all right, 222, 10, 10, 4, C is 6, okay, D is 14, 2, E is 18, -4. The residual for which of the 5 points has the largest absolute value? Okay, so when I look for a line of best fit between these numbers, and I did a pretty good job of graphing this. This is my phone case here. It looks like my line of best fit would be somewhere like this. It seems pretty obvious to me that B is the furthest from my line of best fit. Okay, so some are a little above, some are a little below, because that's what the line of best fit does. It minimizes the sum of the squares. It minimizes the sum of the squares, the area of these residuals. And so it's pretty obvious to me it's B. And if you need more help on this question, I'm happy to help, but it appears that B is the furthest from the other lines. Okay, last one. Let's take a look. For a biology project, you want to measure in weight, in grams, the tail length, and the equation is this. So we want to predict the tail length and 3 times the weight. So if you tell me the weight, then I can multiply by 3 and add by 20 and tell you the predicted tail length. So it says a mice that weighs 0 grams will have a tail length of 20. Which of the following is not correct? Well, if we plug in 0, a mouse that weighs nothing, it's going to have a tail length of 20. Well, hypothetically, yes, that's true, but that's got to be false because a mouse that weighs nothing doesn't exist. If you need more help on understanding why each of these are true, please let me know. Thanks for joining us. Have a good one.